Okay, so this is the thermal behaviour bit, and today we're going to be working on defining and applying the concept of specific heat capacity, selecting and applying the equation Q equals mc delta T, or MCAT, and describe an electrical experiment to determine the specific heat capacity of a solid or a liquid. Right, so entropy. What is entropy? That's the first thing I'm going to cover today. It's not particularly spec relevant, but I think it's really important that you understand it. So entropy, I think, is a really overused word. The physical definition of entropy is a thermodynamic quantity representing the unavailability of a system's thermal energy to be converted into mechanical work. This is often interpreted as the degree of disorder or randomness that the system is currently in. A perfectly crystalline substance at 0 Kelvin or absolute zero will have no entropy, and so that is the least disordered or most ordered or least random system with the highest capacity to convert its energy into mechanical work. All of its energy, all of its thermal energy. Funnily enough, it doesn't have any thermal energy at that state because it's got 0 Kelvin. And that is the key point here. Thermodynamics centers around inefficiency. Everything in thermodynamics is really a statement of inefficiency. You can't do any process 100% efficiently unless at the very extremes when you can't do the process anyway. Interestingly, entropy will always rise in spontaneous interactions. Now, this is used to explain all sorts of things, sort of semi-physically. It's quite a cool notion that the world is sort of tending more and more towards disorder, but it's pretty obvious as well. Like, you don't have to be Brian Cox flying out into the desert and dropping sand on the floor to show that. Anyway, so heating materials. Now, when you provide heat to a material, its temperature can rise, right? Obviously, when I say can rise, it's a can rise rather than will rise, because obviously it will depend on whether it's going through a state change. But presume it's not going through a state change, what will it be dependent on? Well, obviously the amount of the substance. More substance will mean it takes more energy to heat it up. The amount of the heat transferred, obviously more energy means more energy has gone into it. And the type of material that it is. Some materials will heat up very easily and some materials will heat up less easily, right? So we can say that the change in T is dependent on 1 over the mass, because it's inversely proportional to that, directly proportional to the amount of heat that you put in, and inversely proportional to some constant of the material. Now, I could have just said proportional to K. There's a reason we picked 1 over, and we'll see that in a minute. Right, where T equals temperature in Kelvin, that's important, where Q equals heat transferred, M equals the mass of the substance, and C equals a constant of the material. Right? And we can state this equation that the change in temperature is equal to the amount of heat transferred over the mass times this constant, right? And we can state that this is called that the C is equal to Q over M delta T, which is basically saying that the energy required, that C is the energy required to increase a mass of 1 kilogram by 1 Kelvin. So that constant tells us that. How much energy is required to increase the mass of 1 kilogram by 1 Kelvin. And obviously it's that if that's 1 joule, then it's 1 joule per kilogram per Kelvin, and it makes C equal to 1, which is nice. So C is basically just equal to whatever the energy is, and that's why it's arranged as that. Anyway, that value is called the specific heat capacity. And that's what this is about today, really. So, in the specific heat capacity equation is normally put in this form. The energy transferred through thermal energy, or heat, is equal to mass times the specific heat capacity times the change in temperature. Now, we say change in temperature. Because it's change in temperature, it doesn't necessarily have to be in Kelvin. It could be the difference in degrees Celsius, because the increments of the Celsius scale are equal to the increments of the Kelvin scale. But normally, play it safe, do everything in Kelvin. Water has an SHC of 4.2 kilojoules per kilogram per Kelvin, which means it takes 4,200 joules to heat up 1 kilogram by 1 Kelvin, right? If I transferred 8,400 joules of heat to 0.25 kilograms of water, it should increase by how many degrees? So pause the vid and work that out if you haven't already worked that out. So you should realise twice the amount of heat, and
I'm getting some water.
remember it was inversely proportional to the mass, so it's 1 over a quarter. So 2 times 1 over a quarter is 8. Well done if you got that. You should have all got that, but there you go, you got it. Right, so determining specific heat capacity. So this is an experiment, a simple experiment to determine the specific heat capacity of basically any material. So using this setup here where we've got usually a 1 kilogram known mass block with 2 bored holes in it, one for an immersion heater and one for a thermometer. And what you do is you cover that in insulation, good insulation to stop any heat losses, and then you connect it to a low voltage DC supply with an ammeter, a variable resistor and a voltmeter across your immersion heater. So close the switch to begin heating the immersion heater, record the initial temperature at the same time. By taking measurements of voltage and current and keeping these constant using the variable resistor, calculate power using P equals IV, where I is current and V is voltage. Take readings of temperature at regular time intervals, right? With your data of the time intervals and temperature, you can calculate Q values by multiplying P and T. If you then plot a graph of Q, which is your heat delivered on the x-axis, against T, which is your absolute temperature on the y-axis, actually it won't be absolute temperature, it'll be temperature in degrees Celsius, I'm sorry about that. The gradient of the graph that you plot, which should be a linear graph, will be 1 over mc. With the known value of the mass of the block, you can calculate C for the material. So that's the mechanism. So, specific latent heat. So the previous video we talked about specific latent heat, but we'll just remind ourselves that it is the energy needed to change a kilogram of the substance through a state. And we can say that the heat energy required is equal to the latent heat times mass. So it's that. Now, if you ever need to calculate the energy of heating a substance from a given temperature up to the point of boiling or melting or condensing or any of them, I just said them both, it's fine. Then through that stage and onwards, you need to take into account the formula Q equals mc delta T and also Q equals ml. Right, so you're basically adding up the energies for each of the steps. Now, what will also often be the case is that the specific heat capacity of a solid won't necessarily be the same specific heat capacity of the liquid, which is important to note as well. So each phase has a separate calculation. Right, so on that note, there you go, there's a question. Have a bash at that question and bring in that question's answer and your whole approach to next lesson. Excellent. Bye.